Welcome to our super friendly breakdown of the extended Euclidean algorithm.
Hi everyone. For my part, I'll be showing you how exactly the extended Euclidean algorithm works by both hand and through a Java code. We kept everything simple with just one example, so it's super easy to understand.
To avoid any confusion, we'll be using one example so you can follow the process from start to finish without getting lost. So now, let's begin.
Before we jump into numbers, imagine this. Sending message, log into your bank account or connect Wi-Fi, everything on that, match protect you. And one of the VIPs behind the scene on that is the extended Euclidean algorithm. The regular Euclidean algorithm finds the GCD of the two numbers. But the extended version is the upgraded supercharged siblings. It finds the GCD and the two secret number x and y. For the time complexity of extended Euclidean algorithm is big O of log of the minimum of A and B, which it means it's blazing fast, efficient with the giant numbers, and perfect for encryption.
Alright, it's my turn. Let's actually try the extended Euclidean algorithm on a real example so it's super easy to understand. We're only using one example so you don't get dizzy jumping from one problem to another. And our mission is to find the modular inverse of 7 modulo 40, meaning we want a number that when multiplied by 7 gives a remainder of 1 when divided by 40. Basically, we're searching for the secret number x such that 7 times x is congruent to 1 modulo 40. So, we run the extended Euclidean algorithm on the pair 7 and 40. We do the division steps, we move down the table, we backtrack, all that good stuff. After all those steps, here's what we got. X is equals to 23, Y equals to negative 4, and GCD equals to 1. Let's double check just to be safe. 7 times 23 is equals to 161. 161 modulo 40 is equals to 1. It works perfectly. Now here's the fun part. A computer solves this problem using the exact same steps division, recursion, and back substitution. So let's look at the Java code that solves the same example, the inverse of 7 modulo 40. Right, now that we've solved the problem by hand, let's check out how a computer does the exact same thing. We're still doing the modulo inverse of 7 modulo 40, just like the earlier, but this time through Java code. First, we got this result class. It's nothing crazy. It just stores three things, the GCD and the values of x and y from the equation ax plus by equals GCD. Next up is the heart of the program, the extended Euclidean method. This thing literally follows the same step-by-step process we use in a manual simulation. The division, the recursion, everything. When b hits 0, that's our base case. Basically, the bottom row of our table. And we return the GCD x equals 1, y equals 0. Then as the function goes back up, we update x and y using the same formula we wrote earlier. X becomes the previous y and y becomes the previous x minus a divide b times previous y. Exact same logic, just automated. Now here's the cool part. The mod inverse method, it takes the result from the extended algorithm and checks if the GCD is 1. If it is, boom, we got ourselves a modular inverse. We also add a little trick to make sure the result is positive, because modular inverse should always be positive. Finally, in the main method, we test everything using the same values from our example 7 and 40. When we run it, the program prints inverse of 7 modulo 40 is 23, which matches our manual solution perfectly. So yeah, the computer isn't doing anything fancy. It's literally the same extended Euclidean algorithm we used earlier, just faster and more consistent. And that's the whole code demo. Super clean, super simple. Let's move on.
Now, I will discuss the assessment of our algorithm, followed by our discussion and closing. We evaluated the extended Euclidean algorithm using the four criteria: the correctness, speed, scalability, and the performance with large numbers. So the results showed that the algorithm consistently produced correct modular inverses, so remained fast across our all input sizes. So and performed well even with large numbers commonly used in cryptography. So when we compared it with other methods, the extended Euclidean algorithm stood out both the fastest and most practical way. So in other algorithms like the binary GCD, they showed that moderate performance Fermat's little theorem worked well, but the only for primes and prime factorization. So extremely slow and practical. And overall, the extended Euclidean algorithm proved to be the most reliable for general use. So the algorithm has several strengths. So it's highly efficient and accurate and most reliable. So it works with any pair of our integers, computers, both the GCD and the modular inverses. So and it plays an important role in RSA key generation. So however, it has also limitations. So it can show down slightly with extremely large numbers. So it cannot be used to encrypt by itself. So and it requires some additional functions such as Euler's totient for RSA. So despite the limitations, so the extended Euclidean algorithm remains a crucial foundation our for secure communication. So that includes my part for thank you for joining us in exploring the extended Euclidean algorithm. So we hope this helped to see how much the simple idea plays a powerful role in encryption in digital security. So this ends our presentation. Thanks for watching. See you next time.
One is the loneliest number that you'll ever do. Two can be as bad as one. It's the loneliest number since the number one.